Welcome to this course on transition metal organometallics in catalysis and biology. We have been talking about olefin polymerization in the last few lectures. More specifically, we have been talking about various classification of polyolefin polymers that are available from various perspectives. In this regard, we have looked into polymer classification from a application point of view, particularly from materials perspective. We have also looked into polymer classification from the process point of view from the chemistry point of view, and then as well as from the mechanism point of view. So, having discussed various forms of polyolefin classification, we are going to now focus on polyethylene and start discussing the various aspects of the polyethylene chemistry, particularly with regard to their preparations, their productions, as well as their discoveries. As we had discussed in our earlier lecture, that polyethylenes primarily are classified based on their densities, and they come in three grades. One is called LDPE, the other is LLDPE and HDPE. Polyethylenes, to be more precise. Are classified based on their densities, and they come in three varieties. Which is low density polyethylene, and these are flexible transparent as a film, then comes LLDPE, and they are also fairly flexible. These are linear low density polyethylene, and they are also fairly flexible. And transparent. And the last in this classification comes HDPE. These are high density polyethylene, they are rigid and appear cloudy to opaque. Now, with regard to the historical perspective on the development of various processes producing each of these polymers. The first actually goes back to this LDPE, which is the first one to be synthesized, or there were processes for these to be synthesized, and Ziegler-Natta catalysis actually came long after that, about 2 decades later. Then the first process, or first few processes, that those were used for making this LDPE. Now, as we had spoken about this classification of polymerization, that polymerization from a mechanistic perspective can go by step growth or chain growth mechanism. All these metal mediated polymerization like Ziegler-Natta, they are coordination insertion polymerization or cationic polymerization, and they belong to the group of chain growth polymer. Now, this chain growth polymer not only can happen with cations, but they can also be equally happen with anions or even radicals, which will lead to polymer through this chain growth pathway. And the oldest low density polyethylene was indeed synthesized using the oxygen as the radical initiator by a company called ICI, Imperial Chemical Industries, way back in 1933. Oldest of the polyethylene was synthesized by ICI, which is Imperial Chemical Industries. In 1933, even today ethylene is polymerized under high pressure pressure less than equals 2800 bar and temperature less than equals 275 in presence of radical initiator like oxygen 0.05% or peroxo compound. Now, these one of the main limitation of a radical process is that this radical process is uncontrolled, usually goes without control, and as a result there is a lot of chain transfer and leading to chain branching and short chain short size chains they appear in the polymer backbone. As a result this LDP low density polyethylene has a poor crystallinity and flexible long side and chains. Radical limitation LDP with low density, poor crystallinity, and long chain long side chain branches, long side chain branching. So, by this radical process there are two limitations. Obviously, this is the first limitation is that this has very long side chain branching, low density, so on and so forth, and the second limitation is extremely high pressure, 2800 bar. So, that is a tremendous pressure under which this radical polymerization of ethylene is taken care of, and because of such a tremendous amount of pressure the reaction also goes uncontrolled, and this is done in presence of a radical containing oxygen or any peroxo compound. However, later subsequently Phillips process came into place, where in 1956 using a chromium trioxide catalyst they could prepare these LDPE under much less pressure in a heterogeneous fashion, catalysis fashion. The heterogeneous catalytic Phillips process by Hogan 1956 performed under lower pressure, about 10 to 30 bar, and delivered HDPE, high density polyethylene. So, there is a improvement in the catalyst structure because HDPE is rigid, high density polyethylene, it has a long chain and they are cloudy to opaque and no branching. So, this Phillips process is improvement over the existing radical process which are used for making the LDPE. The Phillips catalyst uses the a pre-catalyst which is a chromium trioxide on a silicon support, uses a pre-catalyst CrO through on silicon SiO2 Al2O3 support. Active site contains chromium 2 and chromium 4 oxidation state. So, in this process the take home message is that a flexible oxidation state change from chromium 2 to chromium 4 is observed in the process which could polymerize ethylene at a much lower pressure of about 10 to 30 bar, as opposed to the radical polymerization which required about 3000 bar, 2800 bar to be more precise, and that too producing polymer which of low crystallinity and low density like LDP, whereas this heterogeneous process using chromium successfully gave HDP in 1956, and this is known as the Philip process. So, before we go into details of this Philip process, let me just note that so far the titanium of Ziegler-Natta catalysis has not entered the arena of ethylene polymerization, and other metals like chromium in this particular case is successfully producing HDPE. So, Philip process. And the process sort of proceeds as follows. On a silicate surface, chromium CrO3 would eliminate in water to give and this in presence of ethylene would give out formaldehyde and reduce the oxygen state of chromium from 6 to chromium 2 as is shown here. And then once this bis-ethylene adduct of chromium 2 is formed. So, this is in chromium 2, and this formaldehyde is obtained by oxidizing these CH2 units for each of these ethylene to give formaldehyde, and chromium getting reduced to chromium 2, which is then coordinated by ethylene, and subsequently these gives a 5-membered chromium metallocycle as is shown over here. Five-membered chromium metallocycle that then beta hydrogen eliminates the way it is shown. To give the chromium compound as is shown here. and this is a chromium hydride species, and during the formation, point to note that chromium now of this oxidative addition of 2 ethylene has changed to chromium 4. Here also it is chromium 4 hydride olefinic species, and that gives, in presence of ethylene, it gives the following corresponding complex, as is shown here. So, this is an allylic compound with and the oxidation state of this remains +4 as well. So, the take home message from this mechanism is that the oxidation state of chromium initially was chromium 6, that changes to chromium 4, then goes to chromium 2 and comes back to chromium 4, and after that it is chromium 4 all the way. So, this is a heterogeneous process in which this high density polyolefin can be obtained at very low moderate pressure, about 10 to 30 bar, and give well behaved high density polyethylene. This chemistry is being done by chromium, which is also early transition metal. Now, a variation of this catalyst is reported by union carbide, that is also a chemical company. Employs chromosine. Chromosine is nothing but a ferrocene equivalent, and this is useful in the sense that low valent chromium this is +2 is directly introduced in polymerization. So, this chromium 2, which was forming from chromium trioxide in the Phillips process, is replaced with chromosine, because that will allow chromium in the divalent state right in the beginning, and the Phillips process. So, that sort of cuts down the reduction of chromium 6 to chromium 4. So, the Phillips process is thus shown over here. So, in presence of hydrogen, chromosine is introduced, and this results in elimination of cyclopentane C5H6, but anchoring the chromium compound onto the silicon surface. So, in this case the chromium has become chromium 4 directly, and also formed this chromium hydride, and hence upon reaction with ethylene, the corresponding polymer product corresponding formula product is formed. This is a nice improvement, where a low valent chromium is directly used for carrying out the catalysis in the union carbide process by starting the reaction with chromosine. So, with this we come to the conclusion of today's lecture. In today's lecture, let me sum up. What we have done is, we have looked into various industrial processes that were available or known at that time for preparing these different grades of polyethylene. For example, the earliest known method for a low density polyethylene or LDPE was reported as early as 1933, in which and later on they are still produced by oxygen as the initiator through radical polymerization, but this requires very high pressure of about 3000 bars, and hence the reaction is extremely uncontrolled, with several long side chains being generated on the polymer backbone. As a result, it gives to low density polyethylene. However, more improved and more tolerable amiable conditions for high HDPE was reported by Phillips process, which was done in a heterogeneous condition, silicate aluminate surface, using chromium trioxide as the catalyst. Chromium trioxide got reduced to chromium 4 and chromium 2 and then to chromium 4, resulting in a chromium metallocycle, and then subsequent coordination insertion polymerization, leading to high density polyethylene were obtained by Phillips process. So, after ICI process for LDPE, then we discussed Phillips process for HDPE, and then we looked on improvement made by union carbide for this chromium catalyst, and instead of using chromium trioxide, which is a high valent chromium precursor to enter the catalytic cycle. The union carbide process uses directly the low valent chromium precursor in form of chromium chromosine, which sort of anchors on the silica surface and then carries out the phthalene polymerization. So, with this I come to an end of today's lecture. We are going to be looking at some more examples at the developmental stage for ethylene polymerization, and then we will cover the most important of all of these ones, the or so called the star of ethylene polymerization, the Ziegler-Natta catalysis, when we meet next. So, once again I would like to thank you for being with me, and I look forward to taking up this topic of olefin polymerization, or mainly ethylene polymerization in great more detail when we meet next. Till then, goodbye and thank you.